Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving deep into one of the most sophisticated aspects of IPsec VPN security: the encryption and decryption mechanisms used in IKE ESP with AES-CTR mode. This is a critical component of modern network security that protects billions of packets traversing the internet every second. Whether you're securing site-to-site VPNs between corporate offices or protecting remote access connections, understanding how AES-CTR works within the ESP framework is essential for any network security professional. Let me start by explaining why AES-CTR mode has become the preferred choice for high-performance VPN implementations. Unlike traditional cipher block chaining modes, CTR or counter mode transforms AES from a block cipher into a stream cipher, enabling parallel processing and eliminating the need for padding. This means we can encrypt and decrypt data at wire speed, making it perfect for modern high-throughput networks where performance is just as critical as security. In this presentation, I'll walk you through the complete journey of a packet as it gets encrypted and decrypted, showing you exactly how the counter values are generated, how the keystream is produced, and how ESP encapsulation works with AES-CTR. We'll look at real-world packet captures, examine the mathematical operations involved, and explore the security considerations that make this mode both powerful and vulnerable if not implemented correctly. IKE and ESP overview. Before we dive into the specifics of AES-CTR, let's establish a solid foundation by understanding how IKE and ESP work together to create a secure communication channel. IKE, or Internet Key Exchange, is essentially the negotiator and key manager of the IPsec world. Think of it as the diplomatic service that establishes the rules of engagement between two VPN endpoints before any actual data starts flowing. IKE operates in two distinct phases. Phase 1 creates what we call the IKE Security Association, or IKE-SA. This is the management channel where both endpoints authenticate each other, agree on encryption algorithms, and establish a secure tunnel for further negotiations. During this phase, you will see protocols like main mode or aggressive mode in IKE version 1, or the streamlined IKE SAINIT and IKE AUTH exchanges in IKE version 2. The beauty of this phase is that it creates a protected environment where we can safely exchange the keys needed for actual data encryption. Phase 2 is where ESP comes into play. Using the secure channel established in Phase 1, IKE negotiates the IPsec security associations that will protect the actual user traffic. These negotiations determine critical parameters, for example, which encryption algorithm to use. In our case, this is AES-CTR. They also determine the key length, the authentication method, and the lifetime of the security association. Each direction of traffic gets its own SA with unique keys, ensuring that compromise of one direction does not affect the other. ESP, or Encapsulating Security Payload, is the workhorse protocol that actually encrypts and authenticates your data packets. When a packet needs to traverse the VPN tunnel, ESP takes the original IP packet, encrypts it using the agreed-upon algorithm and keys, adds authentication data to ensure integrity, and wraps everything in a new IP header for transport across the untrusted network. At the receiving end, ESP reverses this process, verifying the authentication, decrypting the payload, and delivering the original packet to its destination. What makes ESP with AES-CTR particularly interesting is how it handles the encryption process. Unlike traditional modes that encrypt block by block sequentially, AES-CTR generates a keystream that can be XO-read with the plaintext, allowing for parallel processing and eliminating concerns about block boundaries and padding. AES-CTR mode fundamentals. Now let's explore the ingenious mechanics of AES-CTR mode and understand why it's become the gold standard for high-performance encryption in IPsec implementations. AES-CTR fundamentally changes how we think about block cipher operations by converting AES into a stream cipher, and this transformation brings tremendous advantages for network encryption. At its core, AES-CTR works by encrypting counter values instead of the actual data. Here's the brilliant part. We generate a unique counter value for each block of data. We then encrypt that counter using AES with our secret key, and then XOR the resulting ciphertext with our plaintext to produce the encrypted data. This means the AES encryption operation never touches the actual data directly, which has profound implications for performance and security. The counter in AES-CTR consists of two main components: a nonce, which is a unique value for each packet, and an actual counter that increments for each 128-bit block within that packet. In ESP implementations, we typically use a 4-byte nonce derived from the ESP packet's SPI and sequence number, combined with an 8-byte block counter. This ensures that even if the same data is sent multiple times, it will be encrypted differently each time because the counter values will be unique. One of the most significant advantages of CTR mode is that it enables parallel processing. Since each block's encryption depends only on the counter value and not on the previous block's ciphertext, we can encrypt or decrypt multiple blocks simultaneously. Modern processors with AES-NI instructions can process 8 or even 16 blocks in parallel, achieving encryption speeds measured in tens of gigabits per second. This is why you will find AES-CTR in high-performance routers, firewalls, and VPN concentrators. Another crucial benefit is that CTR mode eliminates the need for padding. Traditional modes like CBC require the plaintext to be a multiple of the block size, adding padding bytes that increase packet size and complicate processing. With CTR mode, we simply generate exactly as much keystream as we need and XOR it with the data, whether that's 1 byte or bytes. This is particularly important in networking where every byte counts toward bandwidth consumption and MTU limitations. ESP packet structure with AES-CTR. Understanding the ESP packet structure is crucial for grasping how AES-CTR encryption is applied in practice. When we look at an ESP packet, we're seeing multiple layers of protection working together to ensure both confidentiality and integrity of the data being transmitted. Let me walk you through each component and explain how they interact with the AES-CTR encryption process. The ESP header starts with the Security Parameter Index, or SPI. This SPI is a 32-bit value that identifies which security association to use for processing this packet. Think of the SPI as a lookup key that tells the receiving device which keys and algorithms to use for decryption. Following the SPI is the 32-bit sequence number. This number serves multiple critical purposes. It prevents replay attacks, helps generate unique initialization vectors for encryption, and ensures packets can be properly ordered at the destination. Next comes the initialization vector, or IV, which in AES-CTR mode is actually the initial counter value. For ESP with AES-CTR, this is typically 8 bytes long and consists of a 4-byte nonce followed by a 4-byte block counter initialized to 1. The nonce is usually derived from the SPI and sequence number to ensure uniqueness across all packets in the SA. This IV is transmitted in clear text because the security of CTR mode doesn't depend on keeping the counter secret, only on ensuring it's never reused with the same key. The payload data is where your actual IP packet resides, and it is now encrypted using AES-CTR. This could be an entire IP packet when using tunnel mode, or just the upper layer protocols in transport mode. The encryption process generates a keystream by encrypting successive counter values. It then XORs this keystream with the plaintext. What is elegant about this approach is that the encrypted payload is exactly the same size as the original, with no expansion due to block alignment. Following the encrypted payload, we have padding bytes if needed, though with CTR mode this is only for ESP protocol compliance rather than cryptographic requirements. The pad length field tells us how many padding bytes were added, and the next header field indicates what type of data is in the decrypted payload, typically IP version 4, IP version 6, or a transport protocol like TCP or UDP. Finally, we have the integrity check value, or ICV, which provides authentication for the entire ESP packet, minus the ICV itself. This is crucial because CTR mode by itself only provides confidentiality, not integrity. The ICV is typically generated using HMACSHA-256 or AES-GMAC, ensuring that any tampering with the packet will be detected. Counter generation and management. Counter generation and management is the heart of AES-CTR security, and getting this right is absolutely critical. A single mistake in counter management can completely compromise the security of your encrypted communications. Let me explain the intricate process of how counters are generated, incremented, and managed throughout the lifetime of an ESP security association. The counter structure in ESP with AES-CTR is carefully designed to ensure uniqueness across all blocks ever encrypted with a particular key. The 128-bit counter block is typically divided into three components: a 32-bit nonce, a 64-bit IV, and a 32-bit block counter. The nonce is usually derived from the SPI to ensure different SAs never use the same counter values. The IV portion often incorporates the ESP sequence number, providing packet-level uniqueness. The block counter starts at 1 for each packet and increments for each 128-bit block of data being encrypted. Here's where things get interesting from an implementation perspective. When encrypting a 1500 byte packet, we need 94 blocks of keystream. This means our block counter will increment from 1 to 94. The system must carefully track this to ensure we never wrap around the counter within a single packet, which would reuse keystream and break security. Most implementations limit packet size or use a 64-bit block counter to make wraparound practically impossible. The sequence number plays a dual role in counter management. Not only does it provide anti-replay protection, but it is also incorporated into the counter to ensure each packet uses a unique set of counter values. When the 32-bit ESP sequence number approaches its maximum value of 2 to the 32-1, the SA must be rekeyed to prevent sequence number wraparound. This is why you will see SA lifetime limits based on both time and packet count in VPN configurations. Modern implementations often use what is called the ESP counter mode specification from RFC 3686, which standardizes counter construction. In this scheme, the counter block consists of a 32-bit nonce, the 64-bit ESP IV, which includes the sequence number, and a 32-bit block counter. This provides 2 to the power of 32 unique packets per SA, with each packet able to encrypt up to 2 to the power of 32 blocks or about 68 gigabytes of data, far more than any realistic packet size. One critical security consideration is ensuring counters are never reused, even after system reboots or failovers. High availability VPN deployments must carefully synchronize counter state between active and standby units to prevent counter reuse during failover events. Some implementations store the last used sequence number in non-volatile memory or use time-based components in the nonce to ensure uniqueness across restarts. Encryption process flow. Let's walk through the complete encryption process flow for an ESP packet using AES-CTR, following a packet from the moment it enters the VPN tunnel until it emerges as a fully encrypted ESP packet ready for transmission. This process involves multiple steps that must be executed in precise order to ensure both security and interoperability. When a packet arrives at the VPN endpoint for encryption, the first step is an SA lookup. The system examines the packet's source and destination IPs, protocols, and ports to determine which security association should handle this traffic. This SA lookup yields critical information, including the encryption key, the current sequence number for this SA, and algorithm parameters. If no matching SA exists, The packet might trigger IKE negotiation to establish one, or it might be dropped depending on the security policy. Next, we generate the ESP header components. The sequence number is incremented from its last value. This must be done atomically to prevent race conditions in multi-threaded implementations. The SPI from the chosen SA is placed in the header, and we construct the initial counter value using the nonce derived from the SPI, the current sequence number, and setting the block counter to 1. Now comes the actual encryption process. For each 128-bit block of plaintext, we encrypt the current counter value using AES with our session key to generate a block of keystream. This keystream block is then XO-read with the corresponding plaintext block to produce ciphertext. After each block, we increment the counter and repeat. This continues until all plaintext is encrypted. The beauty of this process is that the AES encryption operations can be pipelined. While one block is being XO-read, the next counter can already be going through AES encryption. After encryption, we add any necessary padding to align with ESP requirements, though CTR mode itself does not require padding for cryptographic purposes. We then append the pad length and next header fields. At this point, we have the complete ESP payload ready for authentication. The authentication step calculates an integrity check value over the ESP header and encrypted payload. It uses the agreed-upon authentication algorithm, for example, HMACSHA-256 or AES-GMAC. This ICV is appended to the packet, providing assurance that the packet has not been tampered with in transit. Finally, we encapsulate everything in a new IP header, using the tunnel endpoints as the source and destination. We then update the checksums and send the packet on its way. Modern hardware can perform this entire process in nanoseconds, using dedicated crypto processors and DMA engines. This achieves line rate encryption even on 100 gigabits per second interfaces. Decryption process flow. The decryption process is where the magic of AES-CTR really shines, because it demonstrates the elegant symmetry of the algorithm. When an encrypted ESP packet arrives at the receiving VPN endpoint, it undergoes a carefully orchestrated series of steps to extract and verify the original data. Let me guide you through this process, highlighting the critical security checks that prevent various attacks. Upon receiving an ESP packet, the first action is to extract the SPI from the ESP header and use it to look up the corresponding inbound security association. This SA contains all the necessary information for decryption, including the AES key, the authentication key, the expected sequence number window, and the algorithm parameters. If no matching SA is found, the packet is dropped and logged, as this could indicate an attack or misconfiguration. Before any decryption occurs, we must verify the packet's authenticity, using the I-circa-V. This is a crucial step that prevents us from wasting CPU cycles by decrypting forged or corrupted packets. We calculate the authentication hash over the received ESP header and encrypted payload. Then, we compare it with the ICV attached to the packet. Only if these match exactly do we proceed with decryption. This authentication check prevents a wide range of attacks, including packet injection, modification, and certain types of denial of service attacks. Next comes sequence number verification, implementing anti-replay protection. The receiver maintains a sliding window of acceptable sequence numbers, typically 64 or 128 packets wide. If the received sequence number falls within this window and hasn't been seen before, we mark it as received and continue processing. Packets with sequence numbers below the window are dropped as potential replays, while packets above the window cause the window to slide forward. This mechanism prevents attackers from capturing and retransmitting packets to confuse or overwhelm the receiver. Now for the actual decryption, which in CTR mode is beautifully straightforward. We reconstruct the same counter values used during encryption, using the nonce from the received IV, combined with incrementing block counters. For each block of ciphertext, We encrypt the counter value with our AES key to regenerate the same keystream used during encryption. XORing this keystream with the ciphertext recovers the original plaintext. The symmetry here is perfect. Encryption and decryption use identical operations, just with inputs swapped. After decryption, we process the ESP trailer to remove any padding and extract the next header field, which tells us how to interpret the decrypted payload. If it indicates IPv4 or IPv6, we have a complete packet ready for forwarding. We perform basic sanity checks on the decrypted packet, such as verifying IP header checksums and ensuring the packet structure is valid. Finally, the decrypted packet is forwarded to its destination, either locally delivered if this host is the final destination, or routed onward if we are acting as a security gateway. The entire process, from packet arrival to forwarding, typically completes in microseconds on modern hardware. Key management in IKE. Key management is the foundation upon which all IPsec security rests, and IKE provides a sophisticated framework for generating, distributing, and managing the cryptographic keys used by ESP. Understanding how IKE derives and manages keys for AES-CTR encryption is essential for anyone implementing or troubleshooting IPsec VPNs. Let me walk you through the intricate process of key generation and the lifecycle of these keys. IKE uses a process called key derivation to generate multiple keys from a shared secret. During the IKE negotiation, both endpoints perform a Diffie-Hellman exchange to establish a shared secret that is known only to them. This shared secret, combined with publicly exchanged nonces and other values, is fed into a pseudo-random function or PRF to generate a master key called SKI seed. From this master key, IKE derives all the keys needed for both the IKE SA itself and the subsequent IPsec SAs. For AES-CTR in ESP, IKE must generate several keys: the AES encryption key for outbound traffic, a separate AES encryption key for inbound traffic, and authentication keys for integrity protection in each direction. The key length depends on the negotiated AES variant: 128, 192, or 256 bits. IKE generates exactly the amount of key material needed by repeatedly applying the PRF to expand the master secret. This process ensures that even if one key is somehow compromised, the others remain secure because they cannot be derived without the original master secret. Perfect forward secrecy or PFS is a critical concept in IKE key management. When PFS is enabled, each IPsec SA rekey performs a new Diffie-Hellman exchange, ensuring that compromise of one set of keys does not affect past or future communications. Without PFS, child SAs are derived from the IKE SA's key material, creating a dependency that could allow an attacker who compromises the IKE SA to decrypt all child SA traffic. While PFS adds computational overhead, it is considered essential for high-security environments. Key lifetime management is another crucial aspect. Keys in IPsec have both time-based and volume-based lifetimes. A typical configuration might rekey after 1 hour or 1 gigabyte of data, whichever comes first. As a key approaches its lifetime limits, IKE proactively negotiates a replacement SA with fresh keys. This rekeying process must be seamless, with the new SA ready before the old one expires to prevent any interruption in traffic flow. During the transition, both SAs remain active briefly to handle in-flight packets. IKE also implements key deletion protocols to ensure keys are properly destroyed when no longer needed. When an SA expires or is manually terminated, IKE sends delete notifications to ensure both endpoints clear the keys from memory. Proper key deletion is crucial for maintaining security, especially in environments where devices might be physically compromised after use. Modern implementations overwrite key material multiple times in memory and may even use special CPU instructions to ensure complete erasure. Security considerations. While AES-CTR mode offers excellent performance and security when properly implemented, there are critical security considerations that network engineers and security professionals must understand. These considerations can mean the difference between a robust, secure VPN implementation and one that is vulnerable to sophisticated attacks. Let me share the key security aspects you need to be aware of when deploying ESP with AES-CTR. The most critical security requirement in CTR mode is ensuring counter values are never reused with the same key. If an attacker can cause counter reuse, they can XOR two ciphertexts encrypted with the same keystream to eliminate the encryption, revealing the XOR of the two plain texts. This is often enough to recover significant information about the original data. In ESP implementations, this is prevented through careful sequence number management and SA lifetime limits, but misconfigurations or implementation bugs could still lead to vulnerabilities. CTR mode provides confidentiality but not integrity by itself, making the authentication component of ESP absolutely essential. Without authentication, an attacker could flip bits in the ciphertext, causing predictable changes in the decrypted plaintext. For example, flipping a bit in the ciphertext flips the corresponding bit in the plaintext, allowing surgical modifications to encrypted data. This is why ESP always combines CTR mode with an authentication algorithm like HMACSHA 256 or includes it in an authenticated encryption mode like GCM. Sequence number management presents another security consideration. The 32-bit sequence number in ESP limits each SA to 2 to the power of 32 packets before it must be rekeyed. In high-speed networks, this limit can be reached surprisingly quickly. A 10 gigabits per second link sending minimum-sized packets could exhaust the sequence space in under 30 minutes. Extended sequence numbers or ESN provides a 64-bit sequence space, but both endpoints must support this feature for it to be used. Side-channel attacks are an emerging concern for AES-CTR implementations. Timing attacks, power analysis, and electromagnetic emissions could potentially leak information about the keys or plaintext. Hardware implementations using AES-NI instructions are generally resistant to timing attacks, but software implementations must be carefully written to avoid key-dependent timing variations. This is particularly important for VPN endpoints processing untrusted traffic from the Internet. The quality of random number generation is crucial for security. The nonces and IVs used in CTR mode must be unpredictable to prevent certain attacks. Weak random number generators have been the downfall of many cryptographic systems. Modern implementations should use hardware random number generators where available or cryptographically secure pseudo-random number generators seeded from multiple entropy sources. Finally, quantum computing poses a long-term threat to current key exchange mechanisms. While AES itself is considered quantum-resistant with sufficient key sizes, the Diffie-Hellman exchanges used by IKE could be broken by future quantum computers. Post-quantum key exchange algorithms are being developed and standardized to address this future threat. Performance optimization. Achieving optimal performance with ESP AES-CTR requires understanding both the algorithmic advantages of CTR mode and the hardware acceleration features available in modern systems. The performance characteristics of AES-CTR make it ideal for high-speed networking, but realizing its full potential requires careful attention to implementation details. Let me share the key optimization strategies that can make the difference between a VPN that struggles at 1 gigabits per second and one that easily handles 40 gigabits per second or more. Hardware acceleration through AES-NI instructions is the most important optimization for AES-CTR performance. These CPU instructions, available on most modern Intel and AMD processors, can perform AES operations in just a few clock cycles. A single CPU core with AES-NI can encrypt at rates exceeding 20 gigabits per second for large packets. The key is ensuring your IPsec implementation actually uses these instructions. Some software stacks require explicit configuration or compilation flags to enable AES-NI support. Parallel processing is where CTR mode really shines compared to other modes, such as CBC. Since each block's encryption is independent, we can process multiple blocks simultaneously. Modern implementations use SIMD instructions to encrypt 4, 8, or even 16 blocks in parallel. Intel's AVX512 instructions, for example, can process 4 AES blocks simultaneously per instruction, quadrupling throughput compared to serial processing. This parallelism extends to multi-core systems, where different CPU cores can handle different packets or even different parts of the same large packet. Buffer management and memory access patterns significantly impact performance. AES-CTR encryption is often memory bandwidth limited rather than CPU limited. Optimizations include prefetching data into CPU cache before it is needed, aligning buffers to cache line boundaries, and minimizing memory copies. Zero-copy techniques, where the same buffer is used from packet reception through encryption to transmission, can dramatically reduce memory bandwidth requirements. Packet aggregation and offloading provide another level of optimization. Technologies like large receive offload and generic segmentation offload allow the system to process larger chunks of data at once, amortizing the per-packet overhead across more bytes. Some network cards now include inline IPsec encryption engines that can handle ESP processing entirely in hardware, achieving line-rate encryption with zero CPU usage. For software implementations, batch processing of packets can improve performance by better utilizing CPU pipelines and caches. Instead of fully processing one packet before moving to the next, efficient implementations might generate keystream for multiple packets, then XOR all packets, then calculate all authentication tags. This approach improves cache utilization and allows better instruction-level parallelism. The choice of authentication algorithm also impacts overall ESP performance. While HMAC SHA-256 is widely supported and secure, authenticated encryption modes like AES-GCM can provide both encryption and authentication in a single pass, nearly doubling throughput compared to separate encryption and authentication operations. Implementation examples. Let's look at practical implementation examples of ESP with AES-CTR across different platforms and programming languages. Understanding how real-world systems implement these cryptographic operations will help you troubleshoot issues, optimize performance, and even implement your own ESP processing if needed. I will show you code examples and configuration snippets from various implementations. In the Linux kernel implementation using the Crypto API, ESP with AES-CTR is implemented through a combination of the especially 4 and especially 6 modules for IPv4 and IPv6 respectively, along with the crypto subsystem. The kernel uses the struct crypto AEAD for authenticated encryption with associated data. When a packet needs encryption, the kernel sets up a scatter list with the packet data, initializes the counter value in the IV, and calls crypto AEAD encrypt. The beauty of this implementation is that it automatically selects the best available implementation, using AES-NI if available, falling back to optimized assembly or generic C code. StrongSwan, which is one of the most popular open-source IPsec implementations, configures AES-CTR through its connection definitions. In the IPsec.conference file, you might see a configuration like ESP equal operator AES-128 CTR-SHA-256 MODP 2048. This specifies 128-bit AES in CTR mode with SHA-256 authentication and 2048-bit Diffie-Hellman. StrongSwan's Karen daemon handles the actual packet processing, using plugins to support different cryptographic backends. These include OpenSSL, kernel crypto, and hardware accelerators. For Python implementations using the cryptography library, you can see how CTR mode works at a high level. The code creates a cipher object with AES and CTR mode, providing a 128-bit counter. The encryptor's update method generates keystream and XORs it with plaintext. While Python isn't suitable for production VPN implementations due to performance, it's excellent for understanding the algorithm and prototyping. OpenSSL, which many applications use for cryptographic operations, provides both EVP high-level and AES low-level APIs for CTR mode. The EVP interface handles the complexity of counter management, while the low-level API gives you direct control, but requires careful counter handling. The command line interface can be used for testing, with commands like OpenSSL-ENC-AES-128-CTR showing the encryption in action. Commercial implementations, like Cisco's ASAA or Juniper's SRX series, use specialized hardware for ESP processing. These devices have dedicated crypto processors that can handle millions of packets per second. Configuration typically involves defining transform sets that specify the encryption and authentication algorithms, then applying these to crypto maps or IPsec profiles. The hardware handles counter generation and management transparently, but understanding the underlying process helps when troubleshooting performance issues or interoperability problems. Troubleshooting common issues. Troubleshooting ESP with AES-CTR requires a systematic approach and deep understanding of how the protocol works. Over the years, I've encountered numerous issues in production deployments, and I want to share the most common problems and their solutions. These troubleshooting techniques will save you hours of frustration when your VPN isn't working as expected. Authentication failures are the most common issue you will encounter, and they manifest as packets being silently dropped after ESP decryption. When you see logs indicating ICV verification failures or authentication errors, the first thing to check is whether both endpoints are using the same authentication algorithm and key. Even a single bit difference in the key will cause every packet to fail authentication. Use debug logging to compare the configured algorithms and ensure they match exactly. Sometimes the issue is more subtle. One endpoint might be using ESP with encryption only while the other expects authenticated encryption. Sequence number issues can cause intermittent packet loss that is frustratingly difficult to diagnose. If you are seeing periodic drops that seem to follow a pattern, check for sequence number window problems. The receiving endpoint maintains an anti-replay window, typically 64 packets wide. If packets arrive out of order beyond this window, they are dropped. This often happens with load-balanced paths where packets take different routes with varying latencies. Increasing the anti-replay window size or ensuring packets follow a single path can resolve this. MTU and fragmentation problems are particularly common with ESP, because the encryption and ESP headers add overhead to every packet. A typical ESP packet adds 36 to 57 bytes of overhead, depending on the algorithms used. If your original packets are already close to the path MTU, ESP encapsulation will cause fragmentation, dramatically impacting performance. The solution is to either reduce the TCP MSS using MSS clamping, enable path MTU discovery, or reduce the MTU on the internal interfaces. Watch for ICMP fragmentation needed messages being blocked by firewalls, as these are essential for PMTUD to work. Performance degradation often stems from CPU limitations when hardware acceleration is not being used. Check whether AES-NI instructions are available and being utilized. The performance difference can be 10 times or more. Use tools like cat/proc/crypto on Linux to see which crypto implementations are available and their priorities. If you are seeing high CPU usage but low throughput, the system might be falling back to software implementation. Interoperability issues between different vendors' equipment can be subtle. While the standards are clear, interpretations can vary. Common issues include different default values for parameters not explicitly configured, disagreements about how to construct the IV for CTR mode, or different behaviors when rekeying. Packet captures on both sides comparing the ESP headers, particularly the IV construction, can reveal these issues. Sometimes enabling explicit algorithm specifications rather than relying on defaults resolves these problems. When packets are being corrupted in transit, you might see intermittent authentication failures or garbage data after decryption. This could indicate hardware problems, but more often it's due to NAT devices or firewalls inappropriately modifying ESP packets. Advanced features and extensions. Beyond the standard ESP with AES-CTR implementation, there are several advanced features and extensions that enhance security, performance, and functionality. These features address specific use cases and challenges in modern network environments. Understanding these extensions will help you design more robust and efficient VPN solutions tailored to your specific requirements. Extended Sequence Numbers or ESN is one of the most important extensions for high-speed networks. Traditional ESP uses a 32-bit sequence number that wraps around after 4 billion packets. On a 100 gigabits per second link, this could happen in just minutes with small packets. ESN extends this to 64 bits, with the lower 32 bits transmitted in the ESP header and the upper 32 bits maintained as state at both endpoints. The full 64-bit value is included in the ICV calculation, preventing rollover attacks. Implementing ESN requires careful state synchronization, especially during the transition when the lower 32 bits wrap around. Traffic Flow Confidentiality or TFC is an advanced feature that obscures traffic patterns by padding packets to uniform sizes and injecting dummy packets during idle periods. With CTR mode, implementing TFC is straightforward since we can encrypt padding as easily as real data. TFC prevents traffic analysis attacks where adversaries infer information from packet sizes and timing. For example, without TFC, an attacker might identify SSH keystrokes or VoIP conversations based on characteristic packet patterns. The trade-off is increased bandwidth consumption, but for high-security environments, this overhead is acceptable. Combined authenticated encryption modes like AES-GCM and CHA-20 Poly 1305 represent the next evolution beyond separate encryption and authentication. These modes provide both confidentiality and authenticity in a single algorithm, improving performance and reducing complexity. AES-GCM uses CTR mode for encryption combined with a Galois field multiplication for authentication, achieving near line rate speeds with hardware support. CHA-20 Poly 1305 offers an alternative for systems without AES hardware acceleration, providing excellent software performance especially on mobile and embedded devices. Multicast ESP extensions enable secure group communication over IPsec. Traditional ESP is designed for point-to-point communication, but multicast extensions allow a single encrypted packet to be decrypted by multiple recipients. This requires sophisticated key management through protocols like GDOI or IKE ESP, where group members share encryption keys while maintaining separate authentication keys. Counter management also becomes more complex, since each sender needs a unique counter space to prevent collisions. Hardware offload capabilities continue to evolve with features like inline TLS/IPsec processing in Smart NICs. These adapters can handle the entire ESP encryption/decryption process, including counter management and authentication, completely bypassing the CPU. Advanced features include large packet offload where the NIC can segment and encrypt jumbo frames into multiple ESP packets, and receive side scaling where different RSS queues handle different SAS for parallel processing. Post-quantum cryptography preparations are beginning to appear in some implementations. While AES-CTR itself is considered quantum resistant, the key exchange mechanisms in IKE are vulnerable to quantum attacks. Hybrid modes that combine classical and post-quantum algorithms are being tested, ensuring security even if one algorithm is broken. The challenge is handling the much larger key sizes. Post-quantum algorithms, for example, can have keys measured in kilobytes rather than the hundreds of bits we are used to with current algorithms. Real-world deployment scenarios. Let me share some real-world deployment scenarios where ESP with AES-CTR plays a crucial role in securing network communications. These examples come from actual production environments and illustrate both the challenges and solutions when implementing IPsec at scale. Understanding these scenarios will help you apply the technical knowledge we have covered to practical situations you might encounter. In large enterprise SD-WAN deployments, ESP with AES-CTR secures the overlay tunnels connecting hundreds or thousands of branch offices. A typical deployment might have a hub-and-spoke topology with regional hubs processing tens of gigabits of encrypted traffic. The challenge here is managing thousands of security associations while maintaining line rate performance. These deployments often use dedicated crypto accelerators or smart NICs with inline IPsec processing. The key design consideration is SA capacity. Each branch requires at least 2 SAs for bidirectional traffic, and with multiple traffic classes, this can quickly exhaust hardware SA tables. Solutions include hierarchical designs where branches connect to regional concentrators, and dynamic SA establishment where tunnels are created on demand based on traffic patterns. Cloud service providers use ESP with AES-CTR for tenant isolation and secure multi-tenancy. In AWS, for instance, the Nitro system uses IPsec to encrypt all traffic between instances and storage systems. Every EBS volume access, every packet between instances in different availability zones, is protected by ESP. The scale here is staggering. Millions of SAs, petabits of encrypted traffic daily. The implementation uses custom silicon with hardware acceleration capable of 100 gigabits per second encryption per chip. Counter management at this scale requires careful design to prevent any possibility of reuse across the millions of active tunnels. Mobile network operators deploy ESP with AES-CTR in their backhaul networks, securing traffic between cell towers and core network elements. With 5G, these links carry massive amounts of sensitive subscriber data at speeds reaching 100 gigabits per second. The challenge is maintaining ultra-low latency while performing encryption. For example, 5G requires end-to-end latency under 10 milliseconds. Solutions include hardware accelerators placed directly in the data path and careful tuning of packet processing to minimize jitter. The ESP overhead must be accounted for in capacity planning, as the 5 to 7% overhead from ESP headers can be significant at these scales. Financial services companies use ESP with AES-CTR for secure market data distribution and transaction processing. Here, the requirements include not just security, but also deterministic low latency and perfect packet ordering. These deployments often use kernel bypass techniques with DPDK or similar frameworks, implementing ESP processing entirely in user space for predictable performance. Timestamp preservation through ESP encapsulation is crucial for regulatory compliance and trade reconstruction. Government and military networks implement ESP with AES-CTR as part of their classified network infrastructure. These deployments often require FIPS 1402 Level 2 or higher certified implementations, with hardware security modules for key storage. Traffic flow confidentiality is mandatory to prevent traffic analysis, and extended sequence numbers are standard to handle high-speed classified data transfers. These networks often implement custom extensions for additional security layers beyond standard ESP. Internet of Things deployments are increasingly using ESP with AES-CTR to secure sensor data and control communications. The challenge here is implementing efficient encryption on resource-constrained devices while maintaining battery life. Solutions include hardware crypto accelerators integrated into IoT chipsets and optimized implementations that minimize memory usage. The relatively small packet sizes in IoT applications make CTR mode particularly efficient since there is no padding overhead. Interoperability testing. Interoperability testing is a critical but often overlooked aspect of ESP deployments. When connecting equipment from different vendors, or even different software versions from the same vendor, subtle incompatibilities can cause frustrating problems. Let me walk you through a comprehensive approach to testing ESP with AES-CTR interoperability, including the tools and methodologies that will save you time and prevent issues in production. The first step in interoperability testing is establishing a controlled test environment where you can systematically verify each aspect of the ESP implementation. Start with basic connectivity using the simplest possible configuration. AES-128-CTR with HMACSHA256, no advanced features. This baseline test confirms that fundamental ESP processing works correctly. Use packet captures on both sides to verify that the SPI values, sequence numbers, and packet formats match expectations. Pay particular attention to the IV format in the ESP header, as different implementations may construct the counter differently. Algorithm negotiation testing ensures that both endpoints can successfully negotiate compatible cryptographic algorithms. Test the full matrix of supported algorithms, including different AES key sizes, authentication algorithms, and Diffie-Hellman groups. Document any combinations that fail and investigate whether it's a configuration issue or a true incompatibility. Some implementations may advertise support for algorithms they don't actually implement correctly, leading to negotiation success but traffic failures. Rekeying behavior is a common source of interoperability issues. Test both time-based and traffic-based rekeying, ensuring that traffic flows seamlessly during the rekey process. Some implementations create the new SA immediately when the old one expires, causing a brief outage, while others establish the new SA proactively. Test edge cases like simultaneous rekey initiation from both endpoints and verify that the implementation handles delete notifications correctly for the old SA. Performance testing under various packet sizes and rates can reveal implementation limitations. Start with large packets at moderate rates, then test small packets at high rates to stress the per-packet processing overhead. Some implementations may work fine at 1 gigabits per second with 1500 byte packets but fail at 100 megabits per second with 64 byte packets due to packet per second limitations. Test with bidirectional traffic patterns, as some implementations have asymmetric performance characteristics. Error handling and recovery testing is crucial for production reliability. Test scenarios like packet loss during IKE negotiation, corrupted ESP packets, sequence number jumps, and replay attacks. Verify that both endpoints properly log errors and recover gracefully. Some implementations may blacklist peers after certain errors, requiring manual intervention to restore connectivity. Test failover scenarios if using redundant gateways, ensuring that SAs can be re-established quickly after failures. Advanced feature compatibility requires careful testing, even when both endpoints claim to support it. Features like extended sequence numbers, traffic flow confidentiality, or multicast ESP may have different interpretations or implementation bugs. Use test vectors from RFCs where available to verify correct implementation. Create specific test cases that exercise edge conditions in these features. Document all findings comprehensively, including packet captures and configuration files, as this information is invaluable when working with vendor support teams to resolve issues. Monitoring and logging. Effective monitoring and logging of ESP with AES-CTR is essential for maintaining security, troubleshooting issues, and ensuring optimal performance in production environments. The challenge is capturing enough information to be useful without overwhelming your logging infrastructure or inadvertently exposing sensitive data. Let me share best practices for monitoring ESP tunnels and the key metrics you should track. Security event monitoring should be your top priority. Track authentication failures, which could indicate attack attempts or configuration problems. Each ICV verification failure should be logged with the source IP, SPI, and timestamp. Patterns of failures might reveal coordinated attacks or misconfigured endpoints. Monitor for sequence number anomalies, for example, replay attempts, sequence number jumps that exceed the anti-replay window, and approaching sequence number exhaustion. Set alerts for when sequence numbers reach 80% of maximum, giving you time to rekey before exhaustion. Performance metrics provide insight into tunnel health and capacity planning. Track packets and bytes encrypted/decrypted per second, breaking these down by SA to identify hotspots. Monitor CPU utilization specifically for crypto operations. High CPU with low throughput indicates hardware acceleration is not working. Measure encryption/decryption latency, especially the 99th percentile, as outliers often indicate problems. Queue depths in the crypto subsystem can reveal bottlenecks before they cause packet drops. Track the ratio of small to large packets, as this significantly impacts performance. SA lifecycle events should be comprehensively logged for security auditing and troubleshooting. Log every SA establishment with details, including peer addresses, negotiated algorithms, and key lifetimes. Rekey events should note whether they were triggered by time or byte count limits. SA deletions should be logged with the reason: normal expiry, administrative action, or error condition. Track failed negotiation attempts with detailed error codes to identify misconfigurations or compatibility issues. For packet-level debugging, selective packet capture with appropriate filters is invaluable. Capture ESP headers without payload data to analyze sequence numbers and identify patterns. During troubleshooting, you might enable detailed logging that shows counter values and keystream generation, but this should never be done in production due to security implications. Use ring buffers for continuous capture that preserves the last few minutes of traffic for post-incident analysis. Correlation of logs across multiple devices provides a complete picture of tunnel behavior. Use synchronized timestamps, preferably with microsecond precision, to correlate events across endpoints. Include contextual information like tunnel names, peer identities, and traffic selectors in log entries. Implement structured logging using formats like JSON to facilitate automated analysis. Consider using correlation IDs that follow a packet through encryption, transmission, and decryption. Long-term trending helps identify gradual degradation and capacity needs. Track daily and weekly patterns in tunnel utilization. Monitor the growth rate of SA establishments as your network expands. Analyze the distribution of packet sizes and how it changes over time. Watch for increasing error rates that might indicate aging hardware or growing attack attempts. Set up automated reports that highlight anomalies and trends requiring attention. Regular review of these trends can reveal optimization opportunities and help predict when infrastructure upgrades will be needed. Compliance and standards. Compliance with cryptographic standards and regulations are crucial when deploying ESP with AES-CTR, especially in regulated industries like finance, healthcare, and government. Understanding the relevant standards not only ensures legal compliance, but also provides assurance that your implementation follows security best practices. Let me guide you through the key standards and compliance requirements you need to consider. FIPS 1402 and the newer FIPS 1403 are cornerstone standards for cryptographic module validation in many countries. For ESP with AES-CTR to be FIPS compliant, both the AES algorithm implementation and the CTR mode must be validated. Level 1 compliance requires correct algorithm implementation, while Level 2 adds requirements for physical security and role-based authentication. Many organizations require Level 2 or higher for VPN gateways. The validation process includes extensive testing of edge cases, error conditions, and known answer tests. Using FIPS-validated crypto libraries like OpenSSL's FIPS module or hardware security modules ensures compliance. Common Criteria certification provides international recognition of security evaluations. ESP implementations are typically evaluated under the Network Device Protection Profile. The evaluation examines not just the cryptographic algorithms but the entire system, including key management, audit logging, and administrative interfaces. EAL4 Plus is commonly required for government deployments, involving source code review and extensive penetration testing. The certification process can take years and cost millions of dollars, but it provides strong assurance of security. Suite B cryptography, defined by the NSA, specifies algorithms for protecting classified information. For ESP, Suite B requires AES-128 or AES-256 in GCM mode, though CTR mode with separate authentication is acceptable in some contexts. Key exchange must use elliptic curve Diffie-Hellman with P256 or P384 curves. While Suite B is being phased out in favor of the commercial National Security Algorithm Suite, many systems still require Suite B compliance. Industry-specific regulations add additional requirements. PCI DSS for payment card processing requires strong cryptography for data in transit, with specific key management requirements. HEPA for healthcare data mandates encryption but doesn't specify algorithms, though AES is universally accepted. Financial services regulations like SWIFT-CSP require annual attestation of cryptographic controls. Each industry has subtle differences in requirements that must be carefully addressed. International variations in cryptographic regulations can complicate global deployments. Some countries restrict key lengths. For example, certain jurisdictions have historically limited encryption to 56 or 64 bits, though these restrictions are becoming rare. Export controls still apply to cryptographic hardware and software, requiring licenses for export to certain countries. The Wassenaar arrangement provides a framework for these controls, but implementation varies by country. Russia and China have specific requirements for cryptographic algorithms used within their borders, sometimes requiring domestic algorithms alongside or instead of AES. Audit and documentation requirements are often overlooked, but are crucial for compliance. Maintain detailed records of algorithm selections, key lengths, and the rationale for these choices. Document key management procedures, including generation, distribution, storage, and destruction. Regular audit of ESP configurations ensures continued compliance as standards evolve. Automated compliance checking tools can verify that deployed configurations match approved standards. Remember that compliance is not a one-time achievement, but an ongoing process that requires regular review and updates as standards and threats evolve. Future developments. The landscape of ESP encryption is evolving rapidly in response to emerging threats, new use cases, and advances in both attacking and defending cryptographic systems. Understanding these future developments will help you make informed decisions about long-term VPN architecture and prepare for upcoming changes in the IPsec ecosystem. Let me share the key trends and developments that will shape ESP with AES-CTR and its successors in the coming years. Post-quantum cryptography represents the most significant upcoming change to IPsec. While AES-CTR itself is considered quantum-resistant with 256-bit keys, the Diffie-Hellman key exchanges used by IKE are vulnerable to quantum computers. NIST is standardizing post-quantum algorithms like Crystal's Kyber for key exchange and Crystal's dilithium for signatures. Hybrid modes that combine classical and post-quantum algorithms are being developed for IKE v2, ensuring security even if one algorithm fails. Early implementations are already appearing in experimental branches of Strong Swan and other IPsec stacks. The challenge is that post-quantum algorithms have much larger key sizes. Kyber public keys, for example, are over 1 KB compared to 256 bits for traditional ECC, requiring protocol modifications to handle larger payloads. Authenticated encryption with associated data modes are becoming the preferred choice over separate encryption and authentication. AES-GCM is already widely deployed, but newer modes like AES-GCM-SIB provide nonce misuse resistance, preventing catastrophic failures if counter values are accidentally reused. CHA-CHA-20 Poly 1305 offers excellent software performance and is becoming standard in mobile and IoT deployments. Aegis, recently standardized, promises even better performance by deeply integrating authentication with encryption at the primitive level. Hardware acceleration is advancing beyond traditional AES-NI instructions. New CPU instructions like Intel's AVX512 AES enable parallel encryption of multiple independent AES blocks. Upcoming processors will include dedicated cryptographic engines that can handle complete ESP packet processing, including header parsing, encryption, and authentication in a single operation. Smart NICs with P4 programmable pipelines allow custom ESP processing offload, enabling features like selective encryption where packet headers remain in cleartext for deep packet inspection while payloads are encrypted. Network function virtualization and cloud-native deployments are driving changes in how ESP is implemented. Containerized VPN gateways need to efficiently share hardware crypto resources. Technologies like SRIOV and mediated devices allow multiple containers to securely access hardware accelerators. The IETF is working on standards for ESP and overlay networks, addressing challenges like double encryption and MTU issues in SD-WAN deployments. Cloud providers are implementing ESP transparently, with some offering it as a network service that requires no configuration from users. Machine learning is being applied both to attack and defend ESP implementations. On the attack side, ML models can analyze encrypted traffic patterns to infer information about the plaintext, even with traffic flow confidentiality. Defenders are using ML for anomaly detection, identifying unusual ESP traffic patterns that might indicate attacks or misconfigurations. Future ESP implementations may dynamically adjust parameters like rekey intervals and packet padding based on ML analysis of traffic patterns and threat levels. Zero-trust architectures are influencing ESP deployment models. Instead of traditional site-to-site VPNs, microsegmentation requires ESP tunnels between individual workloads. This drives requirements for automated key management, dynamic SA establishment, and integration with identity systems. Standards like IETF's Group 1 KEV2 are evolving to support these use cases with efficient group key management and policy distribution. The future of ESP is not just about faster encryption but about more intelligent, adaptive security that responds to the evolving threat landscape. Best Practices Summary. After exploring the technical depths of ESP with AES-CTR, let me consolidate the most important best practices that will ensure your deployments are secure, performant, and maintainable. These recommendations come from years of real-world experience and represent the collective wisdom of the security community. Following these practices will help you avoid common pitfalls and build robust VPN solutions. For algorithm selection, always use AES-256-CTR for new deployments unless you have specific regulatory requirements for different algorithms. While AES-128 is still considered secure, the performance difference is negligible with modern hardware, and AES-256 provides better long-term security margin. Always pair CTR mode with strong authentication HMACSHA-256 at minimum, though AES-GCM provides better performance if both endpoints support it. Enable perfect forward secrecy to ensure that compromise of long-term keys doesn't affect past communications. Use Diffie-Hellman groups of at least 2048 bits for RSA or 256 bits for ECC. Key management requires careful attention to both security and operational aspects. Implement automated key rotation with SA lifetimes of no more than 8 hours or 10 GB of data, whichever comes first. Use hardware security modules or key management services for storing master keys in production environments. Never use pre-shared keys in production. Always use certificate-based authentication for IKE. Implement proper key deletion procedures, ensuring keys are overwritten in memory when SAs are terminated. Monitor key usage and set alerts well before lifetime limits are reached. Performance optimization should be approached systematically. Always enable hardware acceleration when it is available. The performance difference can be 10 to 100x. Use CPU affinity to bind crypto operations to specific cores, reducing cache misses. Implement packet aggregation and jumbo frames where possible to reduce per-packet overhead. Consider using receive-side scaling to distribute ESP processing across multiple CPU cores. Monitor performance metrics continuously and establish baselines for normal operation. Configuration management and documentation are essential for maintainability. Use configuration management tools to ensure consistent settings across all endpoints. Document all algorithm choices, key lifetimes, and policy decisions. Implement version control for configurations and maintain a changelog. Create runbooks for common operations like adding new tunnels or troubleshooting authentication failures. Regular configuration audits ensure compliance with security policies. Testing and validation should be comprehensive and ongoing. Perform interoperability testing before deploying new equipment or software versions. Regularly test failover and recovery procedures. Conduct penetration testing specifically targeting your ESP implementation. Use packet captures to verify correct ESP packet formation and counter management. Implement automated testing for configuration changes before they reach production. Remember that security is an ongoing process, not a destination. Stay informed about new vulnerabilities and patches. Regularly review your security posture, and be prepared to adapt as the threat landscape evolves. Conclusion and resources. We've completed our deep dive into the technical intricacies of ESP with AES-CTR mode, covering everything from the fundamental cryptographic operations to real-world deployment challenges. This knowledge forms the foundation for building and maintaining secure, high-performance VPN infrastructures that protect critical communications in today's interconnected world. Throughout this presentation, we've seen how AES-CTR mode transforms block cipher encryption into a stream cipher, enabling the parallel processing and performance characteristics that make it ideal for network security. We've explored the careful dance of counter management, where a single reused value could compromise security, and the elegant simplicity of XOR operations that provide confidentiality at wire speed. The integration with ESP adds layers of complexity but also provides the framework for authenticated, replay-protected communication channels. The key takeaways you should remember are: first, counter uniqueness is paramount. Never allow counter reuse within an SA lifetime. Second, always combine encryption with authentication, as CTR mode alone does not provide integrity protection. Third, hardware acceleration makes a dramatic difference in performance and should be used whenever possible. Fourth, proper key management, including regular rotation and secure storage, is essential for maintaining security over time. And finally, thorough testing and monitoring are crucial for identifying and resolving issues before they impact production traffic. As we look to the future, ESP with AES-CTR will continue evolving to meet new challenges. Post-quantum cryptography will require protocol updates to handle larger keys and different mathematical foundations. New authenticated encryption modes will provide better performance and stronger security guarantees. Hardware acceleration will become even more sophisticated, with inline processing eliminating CPU overhead entirely. And automation will increasingly handle the complex task of managing thousands or millions of security associations in cloud-native environments. I encourage you to apply this knowledge in your own environments, whether you are securing a small branch office connection or architecting a global SD-WAN deployment. Remember that security is not a destination but a journey. Stay informed about new developments, regularly review and update your implementations, and always be prepared to adapt to emerging threats. For further learning, I recommend studying RFC 3686 for the ESP counter mode specification, RFC 7296 for IKE v2 details, and RFC 4303 for the complete ESP protocol. Thank you for your attendance. Please consider subscribing to the channel.